If dark matter is puzzling, then dark energy is a complete enigma. This major component of the universe was discovered in 1995 by observations of distant supernovae. As mentioned previously, supernovae are enormously important distance indicators. When a star brightens to rival the light of an entire galaxy, it can be seen for billions of light years away. And when that star's death has a fixed amount of energy associated with it, it can be treated as a standard light bulb or a standard explosion in the universe, enabling us to measure the distance to a far-off galaxy. Let's follow the story of the expanding universe, or astronomers' attempts to trace this back further out in space and further back in time. Hubble's measurements were made within a few 100 million light years of the Earth. That's a small fraction of the age of the universe. He saw a linear Hubble relation, and that was enough to implicate the fact that there had been a time when all the galaxies were on top of each other and the universe formed. By the mid-1990s, astronomers had traced Hubble's expansion out hundreds of times further and to hundreds of times larger redshifts than Hubble managed, using larger and larger telescopes. They saw a continuation of the same linear relationship between distance and velocity, extending now out to distance of 1 billion light years or more. But then, and even before, astronomers speculated that they should see something interesting. When galaxies were closer together, their mutual gravity was larger. So whatever caused the initial expansion, the expansion rate should be slowing because of the mutual gravity of galaxies acting on each other. Therefore, the universe should be decelerating in its expansion rate. If we invert this logic and consider looking out in space and therefore back in time, previously we should expect to see the universe expanding faster than it is now, because it's been decelerating. As astronomers gained the ability to use supernovae to trace the distances and redshifts of even more far-off galaxies, distances of several billion light years, they anticipated seeing the slope of the Hubble relation steepen, the expansion being faster, or at least the same speed in the past. What they saw was the complete opposite. They saw that the expansion rate in the distant past was actually slower, meaning the universe has accelerated in its speed. This was not just a surprise, it was completely inexplicable. The force of gravity should act to slow down the expansion. Nobody could think of a force that would make the expansion speed up. Two groups were working on this, and they were in mostly gentle and polite competition. One led by Adam Rees at the Space Telescope Institute, and the other led by Saul Perlmutter at Lawrence Berkeley Lab. Their result, an apparently accelerating universe, was so surprising, so shocking, and so unanticipated that each group questioned their own results. They checked each other, they compared samples, and they went off and gathered new measurement. But the results stubbornly persisted. The universe seems to be accelerating in its expansion rate. Let's be clear on the logic of this observation, since it's the only underpinning for the measurement of dark energy. What these teams observed was that distant supernovae were 20 or 30% fainter than they expected. They inferred from that these supernovae were further away than expected in a model where no dark energy was present. So something extra in the model was needed to take these supernovae to larger distances. That would be the acceleration they observed. The observation just talks about acceleration. It says nothing about what causes it or the physical nature of that, but the phrase dark energy was quickly applied to the entity causing the acceleration. It's something akin to anti-gravity because it works in the opposite sense of gravity, to force the universe to move faster and faster. As these groups pushed the data and their observations to newly faint levels, they were actually able to trace back through the phase of acceleration, which has lasted the most recent 5 billion years, to the earlier phase when the universe was decelerating. The result of this discovery is that the major components of the universe that describe its behavior in the past and on into the future are both mysterious. One is dark matter, which acts to counteract the expansion, and the other is dark energy, acting to increase the expansion rate. It's as if the universe has a brake and an accelerator. Combining different measurements to see simultaneously the strength of these two components, the presence of dark energy dominates dark matter by a factor of 2, which is why the universe is currently accelerating. In the decade or more since the dark energy discovery, the level of measurement has increased, but the basic result has not gone away. Indeed, it has strengthened. There is an indirect argument for dark energy as well as the direct argument based on supernovae. The indirect argument is the observation from the early universe, using microwaves, that space is flat. Although general relativity allows the universe to be curved on very large scales, positively or negatively, it seems to be flat. That flatness of space can only be explained if the universe contains more than the dark matter we see with our observations. Dark energy appears to be necessary to explain flat spacetime. We have a situation where the first two-thirds of the universe are governed by dark matter and a decelerating expansion rate. The strength of dark matter diminishes with time because of the dilution of that matter in expanding space. Essentially, the space density of dark matter declines as the volume increases. Dark energy appears to have the particular attribute that it's invariant with time and space, so the strength of dark energy hasn't changed since the Big Bang. And as dark matter got diluted, dark energy started to take over. This happened about 5 billion years ago, and since then the universe has been accelerating. Since dark energy will continue to dominate the cosmic expansion, we don't anticipate that this acceleration will ever reverse. After nearly 20 years, the supernova result is the only direct measurement of something we'll call dark energy. As for what dark energy is, neither physics nor astrophysics provides an answer. As with dark matter, dark energy is beyond the standard model of particle physics. Although physics accommodates the idea of energy in the vacuum, that energy doesn't have the right attribute or strength to explain the accelerating universe. To do more ambitious experiments are being designed, which will improve our measurement of dark energy by an order of magnitude. In particular, they will measure something called the equation of state of dark energy. We will learn whether dark energy is invariant across time and space, and also what the relationship between the pressure of dark energy and its density is. Astronomers have planned something called the Joint Dark Energy Mission, a project of the Department of Energy and the National Science Foundation, with NASA also contributing, an ambitious probe to measure dark energy with better accuracy than at present. It's a multi-billion-dollar mission currently unfunded. Why is dark energy so puzzling for physicists as well as astronomers? Physics contains the concept of energy in the pure vacuum of space. Quantum theory says that the vacuum is not truly empty. There's a tiny residual amount of quantum energy, a half h nu, in quantum theory. But if you work with the quantum theory to calculate what that amounts to on very large scales in the universe, there's a real problem. The amount you calculate is off by 100 or 120 orders of magnitude. It's too large. In other words, the physicist's concept of vacuum energy is ridiculously strong compared to the delicate amount of vacuum energy causing the accelerating expansion. The second puzzle about dark energy is why the universe observed presently has such a close balance between dark matter and dark energy. They're fundamentally different, yet in the entire 13 billion year history of the universe, this is the only time at which they would be similar within a factor of 2. For most of the distant past, dark matter far dominated dark energy, and for the foreseeable and infinite future, dark energy will far dominate dark matter. The fact that they're so close in strength now seems to be a coincidence, and yet they're physically unrelated as far as we can tell. Is there some deeper theory that explains this coincidence or relates dark matter to dark energy? At the moment, we have no idea. With dark energy, we're left with far more questions than answers. Our observational traction on the issues are slender. Astronomers are having trouble coming up with new experiments that'll let us learn about dark energy in more detail, except to decide whether it varies in time and space. Physicists, meanwhile, are speculating theoretically. There are perhaps 300 papers a year written about dark energy. Unfortunately, very few ways to test those ideas. Some of them involve superstrings or supergravity, quantum theories of gravity that unify the four forces of nature. Such speculative physics is far beyond the realm of astronomical observation. Constraining these frontier theories in physics is difficult for simple reasons of particle physics. If we imagine the vacuum, it's been known for decades that the vacuum can generate energy in the form of particle-antiparticle pairs. These appear and disappear on tiny timescales. So to calculate the potential of the vacuum for the creation of particle-antiparticle pairs involves an incredibly complex calculation of all the possible particle-antiparticle pairs and their myriad branching points. Physicists are working on these problems, but at the moment we're no closer to understanding what dark energy truly is. Conceptually, there are several possible outcomes for the universal expansion. In a universe with just matter and dark matter, the possibility exists that there's sufficient mass for the expansion to reverse and the universe to collapse in a big crunch. Present observations essentially rule that out as an outcome. Another possibility is that the universe continues to decelerate at an ever-decreasing rate, coasting to a maximal size in the infinite future. That outcome also seems to be ruled out by observations. Rather, the dominance of dark energy indicates that the acceleration we see now will continue for the infinite future, carrying the galaxies faster and faster apart from each other. That's actually a bleak prognosis for extragalactic astronomy, because at some point the galaxies will be carried away from each other faster than the speed of light, and so be removed from the view of our telescopes. I'm an extragalactic astronomer, so I'm having fun while I can. In a few billion years, it may not be possible to observe any other galaxies. Dark energy is even more mysterious than dark matter, and it dominates the cosmic expansion. Dark energy was implicated by observations of supernovae 18 years ago. Those observations have been confirmed, and we're now confident that the universe is accelerating because of some entity that works opposite to gravity, essentially repulsive instead of attractive. Physics provides no assistance. Simple calculations of vacuum energy get wrong by many orders of magnitude the physical effect required to explain the accelerating universe. There's also the matter of the coincidence of the near equivalence of the strength of dark matter and dark energy, which only occurs once in the history of the universe.